Good day everyone. Welcome to the lecture series on power electronics. In this session we shall discuss single phase full converter with M2 connection with continuous load current. Circuit diagram for single phase midpoint converter or single phase full converter with M2 connection is shown here. So it is a transformer between load and the source, and that is center tapping, or that is midpoint tapping on secondary side is shown in this figure, in this circuit diagram. Input side it is supplied with AC voltage source, single phase AC voltage source. Secondary side we have two parts in the winding, upper part and lower part. Voltage across upper part with this polarity, that is VAN, is equal to Vs, and voltage across the lower part with given polarity is VNB, which is also equal to Vs, and it is sinusoidal voltage, so Vs is equal to Vm sin omega t. Because supply is sinusoidal, the voltage across secondary are also going to be sinusoidal in nature, so Vs is equal to Vm sin omega t. And VBN, what about VBN? VBN is equal to minus Vs, so that is shown this way. So Vs is equal to Vm sin omega t, and V peak value is equal to Vm, and VBN, so VBN is equal to minus Vs, so that is shown with the dotted curve, so that is this way. Now voltage across thyristor 1 and 2 are taken as Vt1 and Vt2 respectively with the given polarity, and current through them from anode to cathode are taken as It1 and It2 respectively with given direction, that is from anode to cathode respectively. Now in positive half cycle, so this VAN is positive, so that is this way. During this period, thyristor 1, because it is the anode of the thyristor 1 is connected to positive terminal of the voltage, so this is positive voltage during positive half cycle, that is connected to positive terminal, it is forward biased during the positive half cycle. So at omega 2 is equal to 0, thyristor 1 is naturally forward biased. Similarly, at omega t is equal to pi, naturally it would be reverse bias, because the anode is connected to negative terminal. So anode is connected to negative terminal, because at omega t is equal to pi, the Vs becomes negative. So it would be naturally reverse bias. At the same time, so VBN is going to be positive. See, at omega t is equal to pi, VBN is becoming positive. At omega t is equal to pi, so this thyristor 2 anode is connected to positive terminal of the voltage. It is going to be naturally forward biased, while this is going to be reverse biased. So this is going to be reverse biased at omega t is equal to pi onwards. So during positive half cycle, thyristor 1 is forward biased. During negative half cycle, thyristor 2 is forward biased. But however, no, they are not diodes, so they are not uncontrolled switches, they are semi-controlled switches. In fact, the turn-on condition can be controlled by the gate current Now, even though thyristor 1 and thyristor 2 are forward biased at the instant omega t is equal to 0 and omega t is equal to pi respectively, so they won't conduct until unless they are fired, until unless they are supplied with the gate current. So let me assume that I am applying gate pulse at omega with some firing angle delay alpha from the instant where they are naturally forward biased. For example, so the thyristor 1 is forward biased at omega t is equal to 0. I am applying the gate pulse at omega t is equal to alpha. Similarly, thyristor 2 is forward biased at omega t is equal to pi. So let me say that I am applying the gate pulse for second thyristor at omega t is equal to pi plus alpha. And same thing I would repeat for remaining cycles also. So I will apply gate pulse for thyristor 1 at 2 pi plus alpha, and for thyristor 2 I will apply gate pulse at 3 pi plus alpha, and so on. So that is this way. So I am applying gate pulses with firing angle delay alpha for each thyristor. So for T1 at alpha, for T2 5 plus alpha, for T1 again 2 pi plus alpha, for T2 once again 3 pi plus alpha, and same thing we repeat. So for simplicity I have considered only 2 cycles of the supply voltage in order to explain the operation of this midpoint converter, full converter. Now at omega t ranging from alpha to pi plus alpha, so thyristor 1 would be conducting, that it would be in forward conduction mode. See here, so I have considered, instead of considering alpha to pi plus alpha, I have considered alpha to pi plus alpha. because I have made an assumption that load current is continuous. So let me assume that load is highly inductive in nature. In that particular case, load current is continuous, and in order to make that continuity, so alpha to pi, anyway, this is already forward biased and it is fired, so it would conduct. At omega t is equal to pi, so this thyristor 2 is still, even though it is forward biased, it won't conduct as there is no gate pulse is given. And load is highly inductive in nature, so it must conduct current even from pi to pi plus alpha. So pi to pi plus alpha. So inductor in this load would make sure that current is still flowing through thyristor 1. Thyristor 1 is still forward biased, is still in forward conduction mode, even at omega t, even after omega t equal to pi. So from pi to pi plus alpha, so thyristor 1 would be conducting, and reason for that is the inductive nature, like highly inductive nature of the load. So omega t ranging from alpha to pi plus alpha, thyristor 1 is in forward conduction state and thyristor 2 is going to be reverse biased. During this period, current would flow this way, and as long as thyristor 1 is conducting, voltage across thyristor 1 would be 0. Thyristor 1 would be 0. So applying KVL for this upper loop, so that is this loop, we can see that voltage across load is same as the supply voltage. So V0 is equal to Vs, and output current is same as thyristor 1 current, and source current, you can see that source current is same as I0. Source current is same as I0, that is same as the load current, because we have only one path. So source current, load current must be same. Source current, load current must be same. So source current is same as thyristor current is same as the load current. So that is shown graphically this way. So this is during this period, omega t ranging from alpha to pi plus alpha, V0 is same as Vs, so that is this, and I0, so because it is load is highly inductive nature, so and it is assumed that load current is continuous, so current is not becoming 0. You can see that current is starting from non-zero, a steady state. So I assume that operation is analyzed at steady state. So at steady state, at omega t is equal to alpha, current is starting from some non-zero value. Already it is been charged, it is having non-zero value, and it will rise slowly as long as you apply the forward positive voltage. So positive voltage is being applied from alpha to pi, so it will rise slowly till omega t is equal to pi, and from omega t ranging from pi to pi plus alpha, so you can see that voltage across load is applied with negative value, and due to this negative voltage, current would start falling. So you can see it is going to fall. However, it never reaches to 0. It fall to a minimum value. In fact, current would rise between omega t ranging from alpha to pi, and it will fall from pi to pi plus alpha, and its minimum value is equal to I min, and let me say maximum value is equal to I max. So it will vary between I min and I max. So this is corresponding to I min, and this is corresponding to I max. So this is maximum value, this is minimum value. And during this particular period, so alpha to pi plus alpha, thyristor 1 is conducting. And during this interval, so Is is same as I0. Is is same as I0, so that is shown. So Is is same as I0, which is same as thyristor current. Now at omega t is equal to pi plus alpha, so what is happening actually? So this thyristor 2 is fired. Thyristor 2 is fired, which was reverse biased. In fact, we can see that during that interval, so during interval alpha to pi plus alpha, this thyristor 2 is reverse biased by voltage minus 2 Vs. Of course, we will see that later on also. So now at omega t is equal to pi plus alpha, what is happening at omega t is equal to pi plus alpha? So already at omega t is equal to pi, it is forward biased. At omega t is equal to t, it is forward biased, but however it won't conduct because there is no gate pulse is applied, and gate pulse is applied at omega t is equal to pi plus alpha. At pi plus alpha, so this forward biased thyristor will be driven into the on state. So load current will be transferred from thyristor 1 to thyristor 2 at this moment. So thyristor 1 is known as outgoing thyristor, thyristor 2 is known as incoming thyristor, because load is transferring from thyristor 1 to thyristor 2. Thyristor 1 is outgoing, thyristor 2 is incoming thyristor. So thyristor 2 is incoming thyristor. So load current would shift from or transfer from the thyristor 1 to thyristor 2 at this moment, that is at omega t is equal to pi plus alpha. In fact, the omega t ranging from pi plus alpha to 2 pi plus alpha during this pi radians, thyristor 2 would be conducting, and load current during this period is same as the thyristor current, which is same as minus of the source current. So you can see during this period, so this is the current path, and you can apply and as thyristor 2 is conducting, voltage across that would be 0, and applying KVL for this lower loop, you can see that V0 is equal to minus Vs. V0 is equal to minus Vs, which is shown by dotted line here. So during period pi plus alpha to 2 pi plus alpha, V0 is same as minus Vs. So that is minus Vs this way. And what about I0? I0 is same as IT2, that is second thyristor current, and that is same as minus of Is. Okay, because here thyristor current, the current through load is downwards. So the current through source is entering into the terminal N here. So in fact, so you can see that source current, so with respect to primary side, if you observe, the source current would be transferred in negative way. So Is is equal to minus I0. Is is equal to minus I0 during this period. So let us indicate these equations graphically in these graphs. So V0 is equal to minus Vs during this range, that is omega t ranging from pi plus alpha to 2 pi plus alpha. You can see, so it is same as minus Vs. And what about current? So current would, in fact, the load will see positive voltage only. You can see that we have rectified output. Even though the source voltage is negative during period pi plus alpha to 2 pi at least, so but load voltage is positive. You can see load will try to maintain the positive voltage as long as you apply good firing angle. So you can see this is the voltage. Of course, it has some negative portion also. So that is from 2 pi to 2 pi plus alpha. That is due to the nature of the load. So whenever load is inductive in nature, so there is a possibility of having the negative voltage for certain amount of period. So that is shown here. So now current would follow the similar shape that was from alpha to pi plus alpha. So similar shape you will have from pi plus alpha to 2 pi plus alpha also, because we have similar pattern voltage applied across the load. So it will rise slowly from pi plus alpha to 2 pi, and then so pi plus 2 pi to 2 pi plus alpha. So during this period load current would fall, and during this period thyristor 2 is conducting, so load current is same as thyristor 2 current. And we know the load source current is same as minus of I0. So minus of this is plus I0, minus of I0 is this way. So source current is going to be negative of the load current. So this is the operation of the single phase full converter with M2 connection for complete cycle. See, I have considered complete cycle pi plus alpha to pi plus alpha to 2 pi plus alpha. So if you consider this particular time period, the duration of this is equal to 2 pi. So this is the operation during 2 pi radians. So one complete cycle. Now same thing would repeat. So same thing will repeat for remaining cycles also. You can see the same thing would repeat for remaining cycles also. See, so for 2 pi plus alpha to 3 pi plus alpha, once again you will have V0 is equal to Vs, and load current would be so this way. So similar to that, similar wave shape, similar shape is that too. From pi alpha to pi plus alpha or pi plus alpha to 2 pi plus alpha. So you will have similar kind of current. So we will have similar kind of operation for remaining cycles also. And even for omega t ranging from 0 to alpha during this period also, because it is assumed that load current is continuous, so load current would follow the similar wave shape. So now this wave shape, so whatever the wave shape you will have this time onwards, that would appear here also. Okay, load current is assumed to be continuous. And during 0 to alpha, omega t ranging from 0 to alpha, you will have this kind of current is flowing through T2 during that period, and source current is going to be negative. So V0 is equal to minus Vs, I0 is equal to I2, and Is is equal to minus I0. So this is the operation of single phase full converter with M2 connection. Coming to the conduction period, you can see thyristor 1 is conducting from alpha to pi plus alpha, thyristor 2 also conducting from pi plus alpha to 2 pi plus alpha. So if you consider this as conduction period, so conduction period in radians, conduction angle in radians, that is equal to pi radians for T1 and T2. both. So conduction angle for each thyristor is same as pi radians. Now let us derive the expression for the input RMS and average value of input and output voltages and currents. Now let us consider the waveforms. So from the operation we know this kind of waveforms we will have for output voltage, output current and source current respectively, assuming current is continuous in nature. Now if you see the source frequency, let me say it is Fs, then load frequency you can see either load voltage or load current. By the time source complete one cycle, load voltage and load current both are completing 2 cycles. You can see the load voltage is repeating for every pi radians. So frequency of load voltage is double to the frequency of the supply. So it is also known as 2 pulse converter, because within one cycle we have 2 pulses of the voltages, so it is also known as 2 pulse converter. So single phase full converter is also known as 2 pulse converter. Now so in order to compute the average value of voltage or RMS value of voltage or current, so we need to consider one cycle of the output voltage or output current, and this is one cycle. So 0 omega t ranging from 0 alpha to pi plus alpha, only this pi radians can be considered because frequency is double. So finding average for one cycle or 2 cycles would result in the same value. So I will compute the average value for alpha to pi plus alpha only, that is sufficient. So consider the value of V0. So consider the mathematical expression for V0 from alpha to pi plus alpha. So now see, the V0 is equal to Vm sin omega t. So V0 is equal to Vm sin omega t, that is same as the source voltage from alpha to pi plus alpha, and it would repeat for every pi radians. So this is the mathematical expression for output. So coming to the load current expression. So in order to find out load current, you have to solve this equation. For example, assuming load is RL type. So this is the mathematical expression for the KVL for load. V0, voltage across load, is equal to R into I0 plus L into di0 by dt. So this is, solving this you will get mathematical expressions for I0. In case it is RLE load, then you will have this KVL, that is V0 is equal to R into I0 plus L into di0 by dt plus E. And solving this equation, one would get the mathematical expression for the load current. And we know relation between load current and source current is this: load current is equal to same as source current for omega t ranging from alpha to pi plus alpha, and that is equal to minus I0. Source current is same as minus I0 for omega t ranging from pi plus alpha to 2 pi plus alpha. Now let us use these mathematical expressions, let us use them and let us try to find average and RMS value of load current and load voltage, source current and source voltage. For input voltage, average value of input voltage, so V0, that is indicated by V0, so that is equal to, so this is the formula. So integrate V0 over one period of the output voltage, one cycle of the output voltage, by time period to complete one cycle, or angle to complete one cycle of the output. Now we know frequency of output is double to that of the frequency of the input. So instead of considering omega t ranging from 0 to 2 pi or alpha to 2 pi plus alpha, so we will consider for only alpha to pi plus alpha only. So because frequency is double, so integrate that for 1 pi radians and divided by pi gives you the average value. So do that. And we know, so during alpha to pi plus alpha, value of V0 is equal to Vm sin omega t. Substitute that, and if you substitute, you will get the average value of output voltage is equal to 2Vm by cos alpha, 2Vm by pi into cos alpha. This is the output voltage. Coming to RMS value of output voltage, so we know RMS value formula is this. So find the integration of the square of the voltage waveform and divide it by the pi radians and apply square root, you will get the RMS value, and if you do so, you will get the value is equal to Vm by root 2, and this Vm by root 2 is same as the RMS value of the input voltage. So and coming to the average value of the output current, so average value of output current can be obtained using this formula. So integrate I0 during this period alpha to pi plus alpha and divide it by pi gives you the average value of the output current. Similarly, average value of the RMS value of output current would be this way. So once again, square So find out the square of I naught and integrate from alpha to pi plus alpha and take its mean, apply square root, that results in the IOR, RMS value of output current. Here one of the important observation for RLE load, so usually we know the voltage across inductor must be 0, right? Must be 0. So average value of voltage across inductor must be 0. According to this fact, you can derive this equation. So V0 is equal to, that is average value of output voltage is equal to battery voltage plus average value of voltage across resistor. Because average value of voltage across inductor, this is always true. And so V0 is equal to I naught into R plus E, where I naught is average value of the load current or the current through resistor. Of course, resistor is part of the load. In fact, current through resistor is same as current through load also. So according to this fact, so according to this mathematical expression, one can say that average value of output current is same as V0 minus E by R in case of RLE load. If it is RE load, for example, in case it is RL load, so in that case battery voltage is equal to 0, so you can substitute E is equal to 0 in this expression in order to get the I naught. So that way one can compute the average value of output current. RMS value of input voltage, that is equal to Vm by root 2, and RMS value of the input current we can see from the waveform of I naught and Is. We can see that Is is equal to I naught from alpha to pi plus alpha of omega t, that is equal to minus I naught omega t ranging from pi plus alpha to 2 pi plus alpha. So now find out its RMS value. So this is the formula for finding RMS value. So you can see from this formula you can see that RMS value of the input current is same as RMS value of the output current. So both are equal. So this way one can find out input and output voltages and current, RMS values and average values. Coming to input power factor, we know the input power factor is defined this way, that is power supply by the source by input VA, and power supply by source is same as power consumed by load in this particular case, because there are no other elements which can consume load power. So there is only load which can consume power, and in the load, in case load is RLE type, then battery and resistor can take power, inductor cannot take power. So consider power taken by the resistor and battery only. No need to consider power consumed by the inductor as it is equal to 0. So now, so what I do, so power absorbed by the load is equal to power absorbed by resistor and power absorbed by battery. Power absorbed by resistor is equal to RMS value of current to resistor square into resistance value. Power absorbed by the battery is equal to battery voltage into average value of current flowing through battery. And we know source voltage is equal to RMS value of source voltage equal to RMS value of the load voltage. RMS value of source current is equal to RMS value of the load current. So substitute them in the formula of input power factor. Input power factor is equal to I naught R square into R plus E into I naught by Vs into Is, where Is is equal to IOR. So substitute that. So this is the way to find out input power factor in general, assuming that load current is continuous in nature. Load current is continuous in nature. In case load current is continuous and ripple free. So what I mean by ripple free current? So current is going to be constant throughout the period, assuming inductance is very large. So load current is almost ripple free. You can assume it is almost constant. In that particular case, you can derive that I naught is going to be average value, which is same as this constant value of load current, which is also same as IOR, that is equal to V naught minus E by R. We know average value of load current is equal to V naught minus E by R. In case current is ripple free, so average current is going to be same as the RMS value of the load current. RMS value of load current. So use that fact. So now in power, we know power is equal to IOR square into E into I naught. So in place of IOR, substitute I naught. And if you further simplify that, you will get P naught is equal to V naught into I naught, and this is true only for ripple free current. In general, this is the formula to compute input power factor. So use this only. But in case if that is it is mentioned that load current is ripple free in the problem itself, so then you can use this formula. So P naught is equal to V naught into I naught. So in that particular case, input power factor is equal to V naught into I naught by Vs into Is. So that is power absorbed by load is equal to same as V naught into I naught, and power, so input VA is equal to Vs into Is, RMS value of input voltage, RMS value of input current. So substitute Vs and Is. So we know Is is equal to IOR, and IOR is same as I0 in case of the ripple free current. So substitute IOR equal to I0, so both will cancel out. So input power factor becomes V0 by Vs. And if you substitute V0 formula and Vs formula, V0 is equal to 2Vm by cos alpha, and Vs is equal to Vm by root 2. If you substitute that, you will get the input power factor is equal to 2 root 2 by pi into cos alpha, where 2 root 2 by pi is equal to 0.9. So it is equal to 0.9 cos alpha. So this way one can find out input power factor. So this is the, please be careful. So please be careful. So this is the general formula to find out input power factor, and this is the formula in case current is ripple free. If load current is constant, then this is the formula. And note that in case of RL load, you can put E is equal to 0, and you can use this formula directly, straight away. You can use this formula by putting E is equal to 0. In case it is battery is absent in the load, so simply it is RL load, you can use this formula. Next one, so let us see how to compute thyristor current also. So thyristor current, we know, so this is the output current, right? It is output current, and from alpha, omega t ranging from alpha to pi plus alpha, thyristor 1 is conducting, and 5 plus alpha to 2 pi plus alpha, thyristor 2 is conducting, and same thing will repeat for remaining cycles also. And these are the thyristor currents. And we know thyristor conduction angle for thyristor 1 and thyristor 2 both are equal, that is equal to pi, radians. So, and if you see, the frequency of output current is so double to the input frequency, but frequency of the thyristor current, if you see it, so you can see it repeats for 2 pi radians. So frequency of thyristor current is same as the supply frequency. In order to compute the average value or RMS value of thyristor current, you have to consider complete 2 pi radians of the omega t. So 2 pi radians of the phase angle. So now by considering that, you can, let us try to find out the average value of or RMS value of thyristor current. So average value of thyristor 1 current and thyristor 2 current both are equal. So simply let me indicate the average value of thyristor current by ITA. So which indicate average value of thyristor 1 and thyristor 2 currents also. Similarly, RMS values also are going to be same. You can see because the wave shapes are similar. So they have same conduction period. And they will have similar kind of wave shape during that conduction period. So and they repeat for every 2 pi radians. So except the time shift, if you see, so IT1 and IT2, I'm sorry, this is IT2. So let me make this correction. This is IT2. I'm sorry. So please note that this indicate IT2. It is not IT1. So thyristor 1 current, thyristor 2 current will have same wave shape with some time shift. So their RMS values and average values are going to be equal. Find out the average value. So using this formula, we know, so in order to find out the average value, you have to integrate this IT1 over complete period, that is from alpha to 2 pi plus alpha. So during this period, so integrate the area under, integrate that, find out area under curve and divide it by 2 pi gives us the average value. So if you do that, no, like you will get that is equal to I0 by 2. You can see if you take 1 by 2 common, so this value is same as the average value of output current. So output current average value by 2 gives us the thyristor average current. Similarly, RMS value of the thyristor current. So once again, use the formula to calculate RMS value. So this way one can compute. So square the current and take its mean value, apply square root. So gives us the RMS value. So do that. And if you do that, so that is equal to under root square root 1 by 2 into, so this value, and this is square of the RMS value of output current, right? So if you take, if you decompose this into two parts, no, 1 by root 2 into under root this value. Under root this value is same as IOR. So it is equal to IOR by root 2. So thyristor RMS current is same as RMS value of output current by root 2. So this way one can find out thyristor currents also. And let us see how to calculate circuit turn-off time. It is very, very important to know circuit turn-off time. In fact, circuit turn-off time should be more than device turn-off time. So circuit turn-off time must be more than device turn-off time. Now let us consider the input voltage and output current waveforms. And from that, let us try to sketch the voltage across thyristor 1 and thyristor 2, and let us see what is circuit turn-off time for each thyristor. So we know generally thyristors are semi-control switches. Turn off in order to turn off them. So after current through they become 0, you have to apply reverse voltage for a period which is known as circuit turn-off time, and the circuit turn-off time should be more than the device turn-off time. So device turn-off time is time required for the device to completely turn off, and the circuit should allow the device to have negative voltage at least for that amount of period. In fact, the circuit turn-off time should be more than the device turn-off time. Let us see. First of all, let us try to sketch VT1 and VT2, and let us see whether what is circuit turn-off time. Let us derive the formula for circuit turn-off time. So from omega t ranging from alpha to pi plus alpha, so thyristor 1 is conducting, and during this period thyristor 1 is conducting voltage across that is equal to 0. And coming to thyristor 2, voltage across thyristor 2, you can apply KVL for this outer loop. It is not conducting. So open circuit voltage across this with this given polarity is equal to minus 2Vs. We know this is equal to 2Vs and this is minus 2Vs, right? So this is minus Vs. So minus Vs is shown with the dotted line. So 2 into that. So during this period Vt1 is equal to 0. So that is shown this way, and Vt2 is equal to minus 2Vs. So this is minus Vs. So minus Vs into 2. So you will have magnitude each and every point of time. So double to that of this curve shown with the dotted line during period omega t ranging from alpha to pi plus alpha. So similarly, omega t ranging from pi plus alpha to 2 pi plus alpha, what would happen? So this thyristor 2 would conduct, right? So load current would transfer from thyristor 1 to thyristor 2. So that is from outgoing thyristor to incoming thyristor. And during this period, thyristor 2 is conducting, voltage across this is equal to 0. And voltage across thyristor 1 would be same as the open circuit voltage, which is equal to 2Vs. Applying KVL for outer loop, you can see. So this non-conducting thyristor voltage would be same as 2Vs. So and let us show that graphically here. So if you show that graphically, see, from omega t ranging from pi plus alpha to 2 pi plus alpha, you can see that voltage across thyristor 1 is same as 2Vs, and we know pi plus alpha to 2 pi plus alpha, this is Vs. So 2 times of this Vs would be same as 2Vs, that is shown this way. So that is omega t ranging from pi plus alpha to 2 pi plus alpha. And during this period, thyristor 2 is conducting, so voltage across that is going to be 0. And same thing would repeat for remaining cycles also. That is this way. So from 2 pi plus alpha to 3 pi plus alpha and 3 pi plus alpha to 4 pi plus alpha, you will have similar kind of wave shape for voltage across thyristor 1 and thyristor 2 respectively. Now if you see here, so this is equal to, this is pi and this is alpha, pi plus alpha. So this is pi plus alpha and this is 2 pi. Now if you consider the circuit turn-off time, so for thyristor 1, so thyristor 1 is reverse bias. After current through that becomes 0, you can see that omega t is equal to pi plus alpha. Load current is shifted from thyristor 1 to thyristor 2. So at this moment, current to thyristor 1 made 0 and reverse voltage is applied immediately. And this reverse voltage would appear across the thyristor 1 till 2 pi. So this is circuit turn-off time period. So this is circuit turn-off period, which is equal to omega into Tc1. And if you want to find out circuit turn-off time, so this angle divided by omega gives us the circuit turn-off period. So Tc1 is equal to this angle by omega, where omega is frequency of supply in radians per second. Similarly for omega 2, so you can see that omega 2 also, omega 2 is reverse bias. You can see that omega 2 is reverse bias at this moment. At omega t is equal to 2 pi plus alpha, you can see that second thyristor is reverse biased and first thyristor is again so forward biased. So at this moment you can see that the voltage across thyristor 2, current through that is becoming 0 and voltage across that is applied in reverse way. And this reverse voltage would appear across thyristor 2 during this period. So that is indicated this way. Of course, same thing is shown here. So omega tc2. So that is circuit turn-off period. Omega T omega into TC2 is given this way, which is also equal to pi minus. Now if you see this phase angle, if you measure this phase angle, that would be is equal to, so 2 pi minus pi plus alpha, which is same as pi plus alpha, pi minus alpha. Similarly, so if you see this instant, so this instant is corresponding to pi and this instant is corresponding to alpha. So this period during which negative voltage is applied across thyristor 2 is pi minus alpha, and omega into Tc is equal to pi minus alpha, So I'm coming to peak inverse voltage across thyristor 1 and thyristor 2. You can see, so this is the inverse peak voltage applied across thyristor 1, which is equal to 2 Vm, and peak inverse voltage applied across thyristor 2 is also 2 Vm in case alpha is less than 90 degrees. In case alpha is more than 90 degrees, then so somewhere here you will have the negative voltage which would be less than 2 Vm. Okay, 2 Vm. So anyway, that we won't consider. Let me assume that alpha is ranging from 0 to 90 only. During for that range of firing angle, the peak inverse voltage is equal to 2 Vm only. 2 Vm only. Okay, so for alpha less than 90 degrees. Let us recall few important points regarding single phase full wave midpoint converter operation. For reliable turn off of the device, circuit turn off must be greater than device turn off time. That is number one point, and we have seen circuit turn off time for each device, that is equal to pi minus alpha. When incoming thyristor is gated on, incoming thyristor is supplied with the gate current, outgoing thyristor is going to be reverse biased by the supply voltage or 2 times the supply voltage. So it is automatically reverse biased, it is automatically turned off. So current through that became 0. So current through outgoing thyristor becomes 0, immediately reverse voltage will be applied. So there is no separate circuit is designed to apply reverse voltage or to turn off SCR. Usually SCRs are semi-control switches. Turn on can be easily controlled by applying gate signal, but turn off you have to go for computation circuit usually. But that is not required for this particular application. So in case of rectifiers, in case of the full converters or half wave converters, whatever. So current through thyristor would become 0 naturally, and voltage across that will be applied in reverse way naturally. So it is also known as natural commutation or line commutation. So these converters are also known as line commutator or natural commutated converters. Okay, rectifier, the converters in rectifier operation are also known as line commutated converters or natural commutated converters. Load current is going to be transferred from incoming thyristors to outgoing thyristors to incoming thyristors when incoming thyristor is gated on. So this is one of the important point. Natural commutation is employed in all phase control rectifier, voltage controllers and cycloconverters. Of course, phase control rectifiers are nothing but the rectifiers what we are discussing right now. Voltage controllers and cycloconverters we shall discuss in the last chapter. So there also we shall see that natural commutation is applied across for each thyristor. So there is no separate commutation circuit is required. However, in case of inverters, in case if you use thyristors for application of inverters or for DC-DC converters, then you may need to design the commutation circuit separately. You may need forced commutation. So commutation means turn off. So turn off process may not happens naturally. You may need to apply the reverse voltage. Peak inverse voltage across each thyristor is equal to 2 Vm for alpha less than 90 degrees. So this is one of the big disadvantage of midpoint converter. So thank you. If you have any doubts, so please approach me through the mail ID given in the description. Thank you.